Welcome to the Shale Across Scales session. I ran a meeting in New Orleans once and I was welcomed. Welcome to Nolans, darling. So welcome. I'm Sue Brantley. I organized this with Carl Stiefel and Chunyun Lee and Jin Gu. Carl couldn't be here. He's at Lawrence Berkeley National Lab, but Chunyun and Jin Gu are up here with me. I'm just going to do a couple opening remarks and then I'll switch into my talk. So we're going to try in this session to look at shales from the deep basin perspective all the way up to the superficial perspective. And I just put this up here because I'm not sure that everybody in the room knows exactly what a shale is, and also because as an earth scientist, I participated once in the chemistry council with Department of Energy, and the chemist asked me, what exactly is a shale? And I realized it's not that easy to explain unless you're a geologist. So a laminated fissile indurated rock with more than 2/3 clay-sized minerals. But I think what's most important perhaps, especially when you're explaining it to a material scientist or to a chemist, is that shales have a history. And this is, there's a great paper that just came out by Don Rimstead and Maddie Schreiber and colleagues in Earth Science Reviews, just looking at sort of a temperature and porosity, sort of a history pathway of what happens to shales. And this is what geologists know, but that's very hard to have a material scientist understand or a chemist understand. And so hopefully that'll come out in this session. Another reason we set this up is that as you know, undoubtedly, there's just been a revolution in terms of energy extraction in this country. And gas shale now is providing as much as 50% of natural gas in the US. And it was as low as 1% in 2000 and 20% in 2010. It's just been happening really rapidly across like almost 30 gas shale plays across the country. And I like to show this because it shows the shale gas wells that have been in place. It cycles through from year to year. And you can see how fast this was in place starting in 2004. And in Pennsylvania, we now have 15,000 of these new shale gas wells that have just been put in place. 25% of the Earth's surface is covered by shale, so that's why we want to look at it from the superficial point of view as well. And critical zone science is now teaching us about how water flows in the subsurface. And I think that these kinds of observations help us even understanding deeper shale as well. So the third reason is there's a lot of interest in this superficial shale. We have the Susquehanna Shale Hills Critical Zone Observatory, which I'll talk a little bit about. The Shale Transect, shales up and down the East Coast that Ashley Deere has been promoting. And then the East River Watershed Function Science Focus Area. And this is partly what Carl Stiefel's been working on, and we wanted to sort of highlight some of those processes. So we have talks this morning, and then there is another session, Shale from Fracking to Forest, with talks tomorrow morning, and then poster in the afternoon. Okay, so that was the opening that Carl Stiefel was going to give, and now I'm going to start my talk. I'm going to try to frame this up and go from depth to the surface. And you can see this is a cross-section of the Marcellus, and this is the kind of fluid flow patterns we're trying to understand. And we want to look at really what happens in the sort of the micro scale that explains some of the properties. So this is Marcellus from depth, and this is Marcellus from at the surface. And my focus is on pores. So shales are rocks that contain more than 2/3 clay-sized grains. And we're very interested in where the water is and where the pores are. Again, from Don Rimstead's paper, 2/3 are phyllosilicates, and the rest are pretty much quartz and feldspar with some carbonates. Interesting paper by Ian Borg talking about these are indurated rocks, but they're fissile, and the more quartz and feldspar, the more brittle the rock is. But then this important concept of the history from weathering, transport, diagenesis, becoming a rock, and then we'll actually talk a little bit about weathering. All right, so let's start at depth in the Marcellus, and then we'll talk about shale hills, which is Rose Hill Shale and Marcellus Shale that are exposed in the Valley and Ridge province of Pennsylvania. And then I'll do a little bit of some shales, very much like the Rose Hill Shale, which is a gray shale, and we'll look across an erosional gradient if I get that far. We're going to use neutron scattering. I'm not really going to explain it. I think Dave Cole will talk about this later. You shoot neutrons through a material, bounces, it scatters off the mineral pore grains. You can see the scattering vector here and then interpret the pore size. When Jingu uses neutron scattering on shales and sends the neutrons through it, if the thin section is in the plane of bedding, you see isotropic scattering. If the thin section is perpendicular, you see anisotropic. And this is really, at heart, the explanation for the facility of the shale. The eccentricity is one way to categorize anisotropy. And this anisotropy, this eccentricity, increases with the alumina content and with the potassium content. So the more phyllosilicated in the rock, the more the anisotropy of these pores, which is related again to this facility. Now, in the organic shales, wherever there's organic matter, we find pores. These tend to be non-anisotropic, so isotropic is a better way to say that, very spherical pores. And you can look at Marcellus in two different parts of Pennsylvania, 25% organic matter. And in this Fib SEM image, you can't even see the tiny pores that are in here. And in this Fib SEM image, you can see it. These pores are water accessible, Jin has shown, and these pores are not. Can we dim the lights in here? I'm not in charge of lights, so I don't know. We didn't even have a podium when we started, so you should be happy we at least have a podium. So just again emphasizing how the nanoscale plays up to the macro scale. This is a log from Terry Engelder from a Marcellus borehole. This is you can actually probably can't see it. Free water that's in here. There's such a tiny amount. There's a lot of gas. That's what this darker color is. And we've actually published a paper suggesting that the tiny bit of water that's in there is brine, and that as the flowback and production water comes out and the total dissolved solids changes with time, once gas is tapped in these boreholes, you can see how it increases with time. We think that it's coming out from the brines in these very tiny pores. So what happens during weathering? I'll show some plots. This is parent composition of the shale, 100% depletion, and this is turned yellow already. I don't think this should have turned yellow already, so I don't know whether we must have set that up wrong. Because I should be talking until... I still have 13 minutes, so I don't know, we'll have to work on that. Okay, so I'm going to show you a bunch of what are called tau plots, and this is 100% parent composition, and then with time, you lose minerals from the surface. This is a case where there is no erosion, and so you get what's called a reaction front until it's 100% gone, and then that moves downward. So this is, let's say, 100% of the illite content, and you've lost like 60% of it, and then as time progresses, 100%, and then that moves downward with time. If you have erosion, the rate that this weathering advances into the rock can be balanced by the rate of erosion, and so you can actually have steady state profiles that look like this. Slow erosion, you can have a very thin reaction front, fast erosion. You still have a reaction front, so this is where all the loss of, let's say, illite occurs, but it's wider, and you never get rid of all the illite at the top. If most of your solute transport across the reaction front is by diffusion, you end up with shallow weathering, and if you have most of the solute transport by advection, you get actually deeper, and that's important in terms of these shales. So what happens in shales and in any weathering rock is porosity starts to be generated, which allows the water to move through and the solutes to transport. And for example, in Marcellus shale, which is high organic matter and high pyrite, you actually, deep in the rock, tens of meters in the rock, you start oxidizing and decomposing the organic matter, leaving behind porosity. So here is the percent pores in different bins. So this, in the deep borehole Marcellus, you have a lot of porosity in that very small, fine size in the organic matter. And as the organic matter decomposes, so this is what the distribution of pores look like in the outcrop. You still have these small pores, but you've actually grown in a lot of porosity because of this organic matter, what still happens in the indurated rock. Since there's pyrite in there, pyrite oxidation actually releases sulfuric acid, dissolving away any calcite that's in there. And so it's really important how much pyrite there is compared to how much carbonate. This ratio determines how much acid is available to actually make to dissolve the minerals. You also have mineral dissolution, so albite dissolution and the pyrite making goethite. And so again, your porosity goes up from unweathered to weathered, and the distribution by pore size is a function of these processes. So what we've seen over and over again in shales is at the deepest depths, sometimes there's production of methane from organic matter, then you get microbial oxidation of organic matter, oxidative weathering of pyrite, coupled to dissolution of carbonate, oxidation of chlorite, weathering of feldspars, weathering of illite, and this is moving up to the surface of the rock. Oh, and then there's also fracturing throughout, which is part of how the water gets down and makes thicker profiles. So here's another one of these reaction fronts. So this is parent all the way down here at 20 meters. This is the Rose Hill Shale, a gray shale, and a little bit of loss of magnesium, so that's only about 30% gone at the top. Same with the Fe2. You can see it in the thin sections, unweathered and weathered. This is the reaction front for chlorite, which is a wide reaction front. Water's moving through it. And if we look at Rose Hill Shale versus Marcellus Shale, we see many of the same features. Here's that chlorite reaction front I just showed you. We see a wider chlorite reaction front in the shale. We also see pyrite loss. So this is parent pyrite composition, loss of pyrite in the Marcellus, very thin reaction front in the Rose Hill. And we've lost our carbonate, lost albite, and we lose a little bit of illite by the top. So just schematically, what we see over and over again is the deep pyrite reaction front coupled with a carbonate reaction front, parent composition 100% loss, a wide chlorite reaction front, and then a little bit of loss of illite at the top. Interestingly enough, shale doesn't all dissolve. You're probably thinking this. Ho-Jin Kim has a poster tomorrow where she shows that a lot of the loss of these clays, like something like 40% of it, is as little tiny particles flowing out up in the soil, but also deeper down in the rock, little particles as the shale breaks apart. Some of this is facilitated in the Rose Hill Shale because there's a high density of fractures in the upper 10 meters. And we can see this with seismic. So this is a seismic velocity line here. This is counts of fractures. And then these data points show, it's a tau plot again, showing 100% illite, loss of illite. And so you can see it with this seismic. So now let's do quickly Shale Hills, Eel River, Fushan. So we're going to increase the erosion rate. And the compositions of these rocks are largely the same. Porosities are largely the same. And yet we see some pretty big differences, and we see some similarities. Again, we see, here's that pyrite reaction front, but we see the same thing in Eel River. Pyrite going to iron oxide, so it's a pseudomorphic transition. We see the same thing at Eel River. If we look at Shale Hills, Eel River, and Fushan, increasing erosion rate, the big thing we see is hardly any microfractures in the Rose Hills Shale. And then we start to see many more microfractures in the upper rock as the erosion rate increases. And this is an open question why these microfractures occur. But everything else is very, very similar. Deep pyrite reaction front, wide chlorite reaction front, illite reacts at the top. What about in 2D? Here's those reaction fronts. What about in 2D? Well, in 2D, we see this pyrite reaction front is actually shallower under the valley. It's very deep under the ridge, shallower under the valley. And we can see some of these reaction fronts with this seismic. That's what I tried to show you in a previous figure. We also know that a lot of the water goes out in this upper reaction front here, much less of the water actually makes it down and explains this chloride front, and then the water gets out even deeper. And this is in the Rose Hill Shale in Pennsylvania. And then if you go to the Eel River, which is Northern California, again, there's that pyrite oxidation front and a little bit of loss of chlorite. But remember, this is the rock that is heavily fractured up here with these microfractures. And so the water in this case actually makes it all the way down. And in Shale Hills, the water goes out here because of all the fractures in that upper 10 meters. But here, the microfracturing goes all the way down, so it actually makes it down to the regional water table. So we're working now with Li and Professor Li and Dacheng Zhao at Penn State, who are creating a reactive transport model of the system. You can see some of the reactions and how we're thinking about this oxygen, making it down through the vadose zone, CO2, and then the entire shale sort of weathering process starting down here where the pyrite starts to oxidize and the organic matter starts to oxidize. So we're hoping to be able to model this with this code. And our initial work on this, these are some output from Dacheng, and he'll be talking about this tomorrow, shows that he can model the system, and there's differences on the south-facing aspect versus north-facing because of the solar irradiation, and he can actually show differences in the depth of weathering that are related to that seem to be what we observe in the real system. So he has, these are actually kind of color contoured tau plots showing reactions of illite, chlorite, and pyrite. And so this is the kind of thing that I think we can ground truth with weathering systems and actually use for deeper systems as well. So just in summary, we're talking about fine-grained materials with fine-grained pores, but they have a history, and I think that that's what we need to understand. The organic carbon hosts a lot of the pores in the Marcellus, and oxidative weathering opens up this porosity with the organic matter decomposing and pyrite oxidizing. A lot of the mass is actually leaving the system in shales, even at depth, as particles. And then these very, very sharp reaction fronts, they actually document where flow changes from vertical to horizontal, and this is important to understand also. So thank you very much. Can you try to figure out how to fix that? Are there any questions? And maybe we can get the next speaker up, please. Who is our next speaker? Is it Chris? Okay, thanks. Do we have a question? You should be getting the next talk up. Can you do that? Any questions? Well, since we'll undoubtedly have a problem with the timing, we'll let you get started early. So the next speaker, I apologize, we're trying to get them to turn the lights down. The next speaker is Chris Neuzil from the U.S. Geological Survey. So there you go.
Thanks, Sue. Thank you and Carl for organizing this session. So the data on what you would call large volumes of rock are rare. They're hard to come by. And I've assembled several of these data in this plot. These are large scale or large volumes of rock, data for large volumes of rock that I judge to be credible values of permeability. So we've got permeability across the horizontal scale, depth vertically. The warm colors, yellow and orange, are for clays and shales. Sue gave a good introduction to what we might describe as clays and shales in this session. And one of the things that jumps out at you from this plot is that clays and shales, and the blues and greens here are other lithologies, including other sedimentary lithologies and crystalline rocks, is the vast difference in permeability between these two types of materials. So for those of you maybe not used to thinking about these things, permeability is basically how easily fluids can flow through this material. And there's something like 6 or 8 orders of magnitude difference, which tells you why the clays and shales have such a profound influence on the hydrogeology flow in the subsurface. And I want to point out to you that there are, in this zone, in this region here, a lot of clays and shales that are what you might call a sweet spot. If you were looking, for example, to host a repository for nuclear waste, they might be of interest to you because not only are they extremely low permeability, but at something like 1 to 10 kilometers in area and under a kilometer in depth, they're kind of accessible and very favorable for that kind of application. So I would ask you whether you might be asking, how do we know that? How do we measure those permeabilities, or how do we estimate them? And in fact, can we? And I'd like to go with that in this talk, show you how we do that, and then I want to take it from that scale down to core scale and compare the two. One of the most interesting and surprising discoveries in the last decade, I would say, is the fact that shales in relatively stable settings around the world, many of these, about half of them, have what I would call anomalous pressures. And when I talk about anomalous pressures, if we think in terms of fluid potential or head, you got seemingly isolated high or low fluid potentials that are in these formations. So you have flow they're either taking on fluid or expelling fluid for reasons that are not immediately clear. And they're all over the world, and as I mentioned, they're in a lot of stable environments. You might expect it in active geologic environments. And if we look at this in at least 2D, you can see, and the red here is supposed to indicate the demonstrable extent of these anomalies, and these are sites where they've been seen in more than one borehole. And the interesting thing, for example, near Bure in France, which is where France's underground lab is that wherever you drill the hole, you seem to find these. So it's unclear whether this is a very extensively anomalously pressured system or not. Also, the lower left, Wellenberg, Switzerland, that's a really large system. And Ontario, Canada, at the Bruce site, I'll talk a little bit more about that in a second, and South Dakota. So if we believe that those pressures are meaningful measurements and that we have these anomalies, and if we believe that Darcy's law applies and that these systems are essentially saturated with water, which I think they are, then there's something going on. And we can, in the simplest way of thinking about it, consider it that there's something either currently some current ongoing perturbation that's causing these anomalous pressures, or there's something that happened in the past and that we're looking at the remnants of what happened. So if we accept these as two descriptions, there are very simple ways of looking at that, and I put these little equations up not for you to remember them, but just to point out that I'm taking a very, very simplified look at explaining these systems. And you can do it with these expressions, these algebraic expressions that are derived from the solutions to the equations describing flow in these systems. And they invariably involved hydraulic conductivity. In this case, we've got a forcing rate. You can consider it, for example, a strain rate and a dimension. Okay, and this is for the case where you have an ongoing forcing, and it may be something subtle that you're not aware of. you can have something in the past. And this is a solution that goes all the way back to Carl Terzaghi in the 1920s. But again, we have hydraulic conductivity. In this case, we're solving for a time, how long these things last, and we've got a specific storage here. If you don't know what that is, don't worry about it. But these are just very simple descriptions that I want to show you. If you use those descriptions to categorize those pressure, both the systems with and without pressure anomalies, in that slide that I showed you before, and you put them into that context, the systems with in red here and without in blue segregate themselves, as you can see in these plots. Hydraulic conductivity on this plot, hydraulic diffusivity is what this is called on this plot, versus dimension. And these curves are for forcing rate. These curves are for time since the perturbation occurred. What you can see is that, as I said, these systems segregate themselves, and what I'll tell you is that this is exactly the behavior you would expect if, in fact, our models were correctly describing these systems, okay, in this very gross and approximate way. And then, so the question you might ask, are these forcing rates reasonable? Are these times reasonable? Well, forcing down here around 10 to the minus 17 per second, that's what you would call stable background strains that you would get from things like erosion, strain rates that you get from something like erosion or background tectonics. So, and up around 10 to the minus 13, this is about what you would see in an accretionary complex where the forcing rates are really high. So I think the forcing rates are reasonable. How about time? Well, what's the most obvious thing that's happened in some of these cases recently, in recent geologic time? That'd be glaciation. So if we look at around 10 to the fourth years, okay, that's almost a dividing line there. So I think these are, in that sense, those numbers are credible. So if we accept that, then we can explain both why anomalies are both present in some systems and not present. We need it to be water saturated for these to work. But we also can say something about the hydraulic conductivity. And we can also be a little bit predictive in the flow over long time scales. And I'll show you an example of that, which is the Bruce site. This is a site in southern Ontario. It's been a little bit contentious because Canada's Nuclear Waste Management Organization wants to build a repository for low and intermediate nuclear waste at this site. You might, by looking at the map, figure out one of the reasons there's been some contention about this. One, it's right on the shores of Lake Huron, and across the lake is Michigan. And so this actually got to head of state level when Justin Trudeau was buttonholed on a visit to Washington not too long ago. But we're on the flanks of the Michigan Basin, several boreholes, including vertical and inclined, and they revealed a really, what I consider an incredible pressure regime in this system. And if we look at it in terms of head, so this is head on the horizontal scale, or potential. First of all, we see that there's a lot of coherence among the boreholes. They give the same pattern, helping increase the confidence. And there's other reasons to be confident of these data. But the thing that floors me is that the hydraulic heads at their lowest are maybe about 200 meters below sea level. Okay, there's no mistaking this as what I would consider a real anomaly. So the obvious forcing in this case is that we've had a glacial, the Laurentide ice sheet, which in this scenario, this is from work done by Dick Peltier at Toronto, there were 3 episodes of ice cover. This has since changed, but we've also used the new scenario with the same findings. So we got both the weight of the ice, and we have deflection of the crust, which bends it, downward with the ice present, that changes the stress regime. And when we incorporate the weight of the ice and the stress from flexure, and we constrain the permeabilities to be about what was measured in the boreholes, which are the yellow, the borehole measurements are the yellow, and the simulation values are shown in red here. If we allow that little bit of play in the permeabilities, we can reproduce with that history, as shown here in the yellow, compared to the red observations in one borehole, we can reproduce these underpressures. So I think I consider a fairly compelling case that that's a reasonable explanation for that system. And we can carry that a little bit further. If we look at the history, we can run this site over with ice, which is shown in this inset here, this little red dot following the ice weight and total stress, and the pressures, or the heads, going up by about 3 kilometers in this system. So that might make you a little bit nervous, but in fact, if you calculate how much flow is in and out of the system, it's really quite small in these cases, even though the pressure excursions are large. So, I would argue to you that there's good reason to have some confidence in these values over here. I've also added in this region here, the region that is occupied by the systems without pressure anomalies. So they've been fairly carefully characterized, but the estimate for the large volume behavior is not as robust, I would say, as in these cases here. But I want to also point out to you now that if we look at, so those are for areas and the thickness of the formation between, say, 1 and 10 kilometers squared. Maybe we can go higher than that, depending on how optimistic you are. But they're smaller areas, and then the orange here is for areas over about 10,000 square kilometers. And what I would say is that looking at these trends, something happens between those two scales, whereby at shallow depths, you don't get the very low permeabilities that you see at smaller scales. So there's some features that are kicking in and increasing the permeability until you get to some depth here, maybe between 1 and 2 kilometers, maybe a little bit deeper. What those are, I have some thoughts about what those are. I won't go into that here. See me after the talk if you're interested. But that's a question. Now, if we want to put this in the context of permeabilities that you might measure in a lab, okay, here we have a plot of laboratory data. That's in the sort of grayed out points that are shown here. Porosity vertical scale, permeability horizontal scale. And the colors are indicating the clay fraction, okay? This is for data that actually took the trouble to report the clay fraction. And you should notice a couple of things. In the lab data, you go from generally high clay contents to less and less clay till finally down at the lowest porosities, the clay contents are down below around 40%, I would say, and I go a little bit lower than you do, so I'd go down to 20% clay here. Now, superimposed on this are the data from these anomalously pressured systems, showing that I would argue that those are basically their permeability at those scales. So we're talking about square kilometer scales over the thickness of the formation look a lot like what you measure in the laboratory, including down to, the agreement with the clay content, which may be fortuitous, is quite good. Now you notice these hatched areas here. These are in the realm that Sue mentioned and that Ian Borg has talked about. When the clay contents are low, which tends to be true at these low porosities, you can get fracturing, and these tend to be shallower and fractured. And let me show you one more plot where we expand the environments we're looking at. We look at geologically active environments and specifically accretionary complexes and the Gulf of Mexico. In fact, what's happening beneath our feet right here, they also tend to fall along this trend, even though they're quite large scale. Okay, these would be in the thousands of square kilometers range, I would say. The colors are not too meaningful in this case because these are representing clay fractions in the upper parts of these systems. We don't really know what it looks like particularly, how it changes, or I didn't find it anyway for these systems, but they all tend to agree. So with that, I will say that I'm happy to take questions. Thank you for your attention.
Okay, we have time for questions. Yeah.
What is it about the high clay content that drives that increase in porosity and permeability?
So the question is, what is it about the high clay content that drives the high porosity? Or what is, I would put it differently, what is it about the change in porosity that correlates with low clay contents? I've talked to people. I mean, it's intuitively pleasing. You lose smectite clays with depth of burial and heating, and you gain, help me out, geochemists in the room, you gain quartz.
Sorry, I was sleeping.
I'm not a geochemist, and I don't even portray one on TV, so I'm still talking to people about why that should be. It's not entirely clear, other than that compaction, heating, diagenesis is you can reasonably expect that to get rid of clays to some degree. But I'm afraid I don't have a really good answer for you.
So you mentioned fracturing. So Sue talked about fracturing in the first couple hundred meters. Are you talking about that too, or are you talking about deeply present fracturing?
Yeah. So the ones that I showed in the I don't know if I can reverse. Yeah. These guys here are relatively shallow. So beyond a kilometer, I don't know that we have any examples with fracturing. I'd have to think about that, but I think not. There is in Japan, there at the Horinobe underground lab, there I think that is the case, but that's a special situation where the fine-grained sediments are mostly siliceous. So they're clay-sized, but not clay minerals, for the most part.
There's another question.
Can you elaborate based on the blue site and the magnitude of those underpressures?
Okay, elaborate on the Bruce site and the magnitude of the underpressures. These are very indurated rocks. They're low porosity, about 8% down to 1% or less. There are several lines of evidence that those pressures exist. One are the measurements that you saw, which are long-term packed off sections that have been monitored for, I'm going to say 3 and more years, depending on the borehole. And the other is results of hydraulic testing, where one of the parameters that were backed out was the original pressure in the system, which gave a similar pattern. So those are two independent sets of data that point to the same pattern. And the other thing is that the gradients in that system are huge. They're on the order of 2 or 4 or 8 or 10, which is almost unheard of in natural systems. Does that address your? I'm sorry? For the Bruce site, I'm sorry, yes. That's the Bruce site, that's Buer, that's Hayes, South Dakota, Esterhazy in Saskatchewan, and Mall in Belgium. So in fact, this one is not these two, I should add, are not anomalously pressured. I misspoke before.
Thank you. I wasn't sleeping. I was worrying about why we can't get the lights to go down and the timer. So if we can have our next speaker up. I wasn't sleeping. I was just worrying actively. Our next speaker is Christophe Tournassat. And I'll get you your talk. And Christophe will be talking about shales and geologic waste repositories from microstructure to macroscale.
So thanks for the introduction. So thanks to the organizers for inviting me for this presentation. So I will talk about the geological waste repository in clay rocks. So as you perhaps know, such type of waste repository is foreseen to occur in deep clay formations, typically between 500 meters deep and 1,000 meters deep. So the clay we are interested in, the clay rock we are interested in looks like this. If you take a bore core, it means it's a fine-grained rock, cemented rock with low water content and low porosity values. And it must be say that for this type of rock under study, so approximately 100% of the porosity is connected. So we know that from, for example, from diffusion experiment of H2O, so water tracers that can access all of the porosity. But the pore network connectivity is made by clay-rich domains. So if you look at this data from Keller et al., that's data obtained from the observation of the microstructure of the clay at the Fib-SEM scale, meaning a 5 nanometer maximum resolution. You can see, in fact, big pores that are disconnected in the structure. But since we know that 100% of the porosity is connected, we know that, in fact, this connectivity is made by the clay-rich domains. So it's explained to partly the low hydraulic conductivity of this clay, and it also explains why we are also mostly interested in this system with the diffusion processes for transport. Because if you plot, for example, the characteristic distance of diffusion and the characteristic distance in red here of advection in such a system with parameters that are in agreement with what can be measured on this type of clay, so you will see that in fact diffusion is it's the dominant process for solid transport in this system. So we are interested in sealing shales, so not brittle shales as shown, so the difference by Chris Neuzil in the last talk. And a typical clay mineralogy we can find in this kind of sealing shale of interest is on the right. So it's a composition that you can find in the Calovian Exfolion in France for Buer repository sites, for future repository sites. So the mineralogy of this kind of clay is mainly made of clay minerals, carbonates, quartz, and other minerals, so accessory minerals such as pyrite and organic matter. But if you look into details in these clay minerals, you will see that it's mostly made by illite, smectite mixed layer minerals, and smectite. So now, what we know about these clay minerals in the system is that they have a very, very high specific surface area, typically for illite. So it's a layered mineral for which you can measure a specific surface area of approximately 100 square meter per gram. For smectite, the specific surface area is even more larger. That's because, in fact, between the layers, water can have access to the pores that are in between the layers, so meaning it's interlayer pores. And so it increases surface area up to 800 square meter per gram. That said, so we are we have this great large surface area, meaning that we can expect large adsorption properties for this system due to these clay minerals, and so we can expect radionuclide retention and retardation, in addition to the fact that diffusion is a main slow process for solute transport. So if we look at the clay structure, in fact, what we have in the network is a substitution of some cations by others, and by others of lesser charge, for example, aluminum by magnesium, or silicium by aluminum in other position. And this so-called isomorphic substitution creates a negative charge of the layer of the minerals, and this is responsible for adsorption of cations in order to compensate the charge. So at the outer part of the particles or in the interlayer space. So cation exchange is studied for a very, very long time. It's one of the oldest sorption mechanism that is known in nature. So we have a very good, in fact, macroscopic view of what is going on. And if we look at the surface, so the surface is negatively charged, so you have an accumulation of, So we have an accumulation of cation at the surface, and we have also the presence, so in the so-called stern layer, and then we have the presence of a diffuse layer where you have an accumulation of cations and a depletion of anions in this volume. So this cation exchange is often non or weakly ion specific, but depending on the ionic strength and background electrolyte composition, then if you are looking at one radionuclide sorption, you can see a big difference in the efficiency of this mechanism. So now we can quantify quite well this process with a very simple model, means the Poisson-Boltzmann equation, or the Gouy-Chapman model that relates a potential, an electrostatic potential to the density of charge in this volume. That's typically what we can plot here. So we have this accumulation in blue close to the surface of the cations, and this depletion in green here of the anions that we can model quite easily. So now we have also for a few years a molecular view thanks to molecular dynamic studies. And what can be said is that last result shows that in fact we have a near agreement with the macroscopic simple Poisson-Boltzmann equation. So for example, in this system, down to interlayer size of 3 water layers, in fact, you can reproduce quite well the profile of anions and cations, meaning that so 3 water layers is 1 nanometer thick interlayer. That's very, very small pore. And we are in agreement. So what I would say the new aspect that has been put forward in the last decade is that the adsorb species are in fact highly mobile in the system. So you have two contradictory things. So you have adsorption, retention, but this adsorption doesn't mean that the species are immobile. So you have also the movement of a species in these porosities, they are not fixed on the surface. So additional mechanism for the retention of radionuclides in this system is a surface complexation. So what happens in fact is at the edges of the clay layers, so termination of the crystal lattice, and you have the presence of amphoteric OH group that can in fact exchange the protons with metals in solution. So that's typically a pH-dependent mechanism that you can find also for oxide that's been really widely described for oxide system like ferrite, goethite, etc. But what is perhaps less well known for clay minerals is that in fact, if you want to describe the adsorption of this part of the system, on these clay edges, you need to consider the whole system, meaning that in fact you have a basal potential at the basal surface and you have edge potential at the edges, but you have a spillover of this first one to the second one. So meaning that in fact you cannot represent the system as a 1D system, but you need to represent the system as a 2D system. And if you try to calculate surface potential of a functional surface charge, so this is a classical DLM model for Zombach and Morel, you can see that for zero charge, you have zero potential. But for clay mineral on the edges, if you have a zero charge on the edges, you have a negative potential because of a spillover effect. So it makes clay minerals more complex than classical oxide. So you have this complex interplay of basal and surface properties, and I must add also that you have a complex chemistry at the surface because you have many many groups present at the surface with different chemistry. So one of the problems is that we get little information from potentiometric titration curve in order to obtain the reactivity of this edge site. So you can see here the curves that you can obtain from this kind of experiment where you titrate protons and hydroxide at the surface. And in fact, the curves are very, very flat. So there is a real difficulty to find specific site reactivity to observe retention properties based on a fitting exercise alone at the macroscopic scale. So fortunately, recently, the group of Liu et al. In Nanjing University in Beijing made a systematic study of the clay edge sites reactivity using first principle simulation, using first principle molecular dynamics simulations. And so they could assign pK value for all of these sites as a function of the chemistry, but also the function of the crystallographic position of these sites. And so from this, it's possible to predict the surface charge as a function of pH and other solution parameters, such as ionic strengths, from first principle. So I believe that in future years, we should be able to model the adsorption and clay-mineral edges from first principle. So for the moment, of course, we need the data to adjust our parameters. So now I've shown you retention models for adsorption of radionuclides. That is really important for radioactive waste disposal. But we need also to couple this retention properties to a transport model. So typically, in order to obtain this kind of curves, where you look at the release of radionuclide as a function of time for a system, and where you try to figure out if the dose rate at a given time is still below your threshold limit that you can apply to the system. If we look at the diffusion experiment that's enabled to obtain some diffusion flux and so some diffusion parameters, here you can see a typical behavior of a clay sample. So you are looking at the flux as a function of the time, and so after a transient state, you obtain a steady state. But you can see that if you look at cations compared to H2O or to anions, so you have cations that are delayed compared to H2O and anions. You have cation steady-state flux, it is larger than H2O steady-state flux, and you have anion steady-state flux that is lower than H2O steady-state flux. And so if you want to explain all of this altogether with the same model, in fact, you will go to the conclusion that a simple Fickian model is not appropriate to explain the results. Of course, you can fit the result with very simple Fickian model, but you cannot explain the result as a whole. So, in fact, we have ample evidence of this problem. So, anions, neutral species, and cations do not have access to the same porosity, so you have to change your porosity as a function of a model if you use just a Fickian model. The parameters value change as a function of chemical conditions, so Fickian model cannot account for this change. In some conditions, we have parameters that are completely unphysical. For example, your pore diffusion coefficient is far larger than the self-diffusion coefficient of the cations of interest in water. And also the retention parameters, so named KD here, that you can obtain from batch experiments do not match with the KD values derived from the diffusion experiments. And sometimes what has been observed is that some diffusion behaviors clearly do not agree with fixed laws. So I will show you this example, a very nice experiment from the group of Plots et al. In Switzerland. So in fact, I have a diffusion cell with two reservoirs, one reservoir with a low sodium chloride concentration, a reservoir with a high sodium chloride concentration, and at time 0, they spiked the same concentration of a radiotracer of sodium 22. And so what you expect if there is no gradient, so fixed law gives you no flux. But what they could observe is that, in fact, you have an accumulation of this tracer in this reservoir and a depletion of this tracer in this reservoir. So it's kind of uphill diffusion process. If you want to explain this, we have to come back, in fact, to the description of what is going on at the clay, at the pore size level. So if we want to do that very simply, we can do this like this. So you homogenize the system and say, okay, the system can be modeled with only one pore size, and in this pore size, you apply both a diffusion law and the fact that you have a cations and anions distribution that follows the Poisson-Boltzmann equation. So if you do that, so it's a very good solution because you can fit all of the data I've shown before, and you can describe anion, water, and cation diffusion in the same manner. So to do that, you have to couple this Nernst-Planck equation. Here there's a efficient term, and this is a diffusion potential term that apply to the system because cations and anions are not moving at the same speed in the system. And you couple this with the Poisson-Boltzmann equation. So you can find plenty of models in the literature using this kind of approach. All of these models have been successful, but the problem is that the description of what is going on in the porosity is not the same for all of these models. So it means that, in fact, the models are under constrained by the diffusion data. And if we want to understand this, we need to consider additional constraints to these models. So one type of additional constraints could come from the effect of the microstructure. So the microstructure of clay samples now can be, in fact, measured, characterized with several types of techniques, bulk techniques like gas adsorption isotherms. Here you have the probability, the cumulative pore volume as a function of pore diameters. The line is this gas adsorption experiment. But you can also make some imaging techniques, like for example with focus ion beam SEM techniques, in order to get the distribution and position and size of the pores in this kind of 3D images. And that's typically what you have with the points here, the dark gray one, that follow this line, this nitrogen adsorption curve nicely, that give you confidence in the thresholding technique you used in order to obtain the information. Now, if we take this information about the porosity fraction as a function of pore width, so you can obtain this such kind of histogram for this clay sample, and you can apply the Poisson-Boltzmann equation and compare what is the effect of a distribution of pore size compared to an homogeneous pore size distribution. And what you can see is that, for example, for the anion accessible porosity, you can have a huge effect as a function of ion strength of this. So usually, if you have a distribution of pore size, you have more access to the anions than if you consider a homogeneous system. So now, we have also some information about the fact that if you have very large heterogeneity in the system at even smaller pore size, so for molecular dynamics, we can infer that for 3 water layers, you can have access of chloride, for example, in the interior pores, meaning 1 nanometer pores. But if you decrease again the pores, like in a very deep clay formation, so you will have, in fact, a complex exclusion of the pores to anions, meaning that only cations and water and neutral molecules can diffuse through this kind of pore. And this can be also seen from experiments. So this kind of experiments made by Chagnot, 2015, is a very nice experiment showing that after the clogging of porosity of the big pores with precipitation of mineral, in fact, you have a decrease of the water diffusibility, but you have a complex suppression of the chloride diffusivity, meaning that you have, in fact, disrupt the diffusion pathway in the biggest pore, and then only the smallest pore can ensure the diffusion, but since they are not accessible to anions cannot diffuse anymore. So we have an importance of microstructure at the clay matrix that scaled down to less than 2 nanometers, in fact. And the problem is that the current techniques for the characterization, no, it's okay, 1 minute. Yeah, okay. So can give you information down to 5 nanometers. So we are really, the next challenge is to obtain with new techniques statistically valid information for smaller pore and to try to include it in reactive transport modeling approach. So my conclusion are that so we have a remarkable improvement in the understanding of integral physics in the past decades, but still the modeling of coupled process is under constraint in the system, and that's for part at least due to sort of microstructure in these models. And so we need to couple this process at all scale to address mechanistic predictive models. I thank you for your attention.
Thank you. I'm afraid we don't have time for questions, but that was great. We can have the next speaker come up. I think so too. Okay, our next speaker is Anastasia Ilgen. She'll talk to us about shale brine CO2 interactions and the stability of caprock.
Good morning. Thank you for coming to my talk. My name is Anastasia Ilgen, and I'm a staff scientist at Sandia National Laboratories. And today I will be talking about the application of shale as caprock for geological carbon storage. So geological carbon storage, as probably most of you know, is a technology that came about to decrease the atmospheric concentration of carbon dioxide. Large volumes of CO2 need to be injected underground and stored for thousands of years to really make a difference. And large volumes are in the megaton scale. So, for a successful storage site, we need to have a large formation that would be fairly permeable and can accommodate those large volumes of CO2, but it also has to be capped to prevent migration of CO2 upwards. And those cap rocks are usually shales because they have low permeability and extensive. At geological storage pressure and temperature, CO2 exists as a supercritical phase, and when it's injected underground, it can set off a series of different reactions, including chemical and physical, because it perturbs the steady state of the system. And so the perturbation include changing the state of stress, pore pressure, temperature, and chemical reactions. The two most typical chemical responses are creation of carbonic acid, acidification of brine, and also dehydration. So when CO2 is injected, it's completely dry, and as it moves underground, it picks up those water molecules and dehydrates the parent mineral assemblage. That can affect porosity and permeability. And so because shales are so heterogeneous and they also are not simple compositionally, there is a huge range. Shales range from silicate rich, quartz rich, to carbonate rich, to clay mineral rich. So we cannot really say with confidence what chemical reactions will take place because they really differ for different mineral assemblages. And those reactions can affect, as I said, porosity and permeability in a variety of different ways with a feedback to the integrity of the caprock and CO2 leakage. So in this study, it's an Energy Frontier Research Center funded by DOE. We look at the how caprock reacts with CO2. We look at the kinetics and products and reactants of those reactions. And the unique part about this is that we're trying to link those chemical alterations to the changes in mechanical properties at the laboratory scales. And we'll look at different lithologies. So we have 3 shales that we're examining. Today I'm only going to talk about Mancos Shale. It's a Cretaceous carbonate-rich shale, which is the most reactive of the series, but we have other shales as well to examine. So just since I'm a geochemist, a few chemical reactions, I'm going to go really quick. So the most typical reactions that people have both documented in the laboratory studies and seen in the field due to injection of CO2 are dissolution of feldspars, phyllosilicate minerals, and carbonates. And carbonates, in particular calcite, has the fastest dissolution kinetics, and it's usually a significant component of shale. It could be up to a few weight percent. So dissolution of calcite can affect porosity at the shorter time scales. And I'm going to show some laboratory results. We use stirred reactors. We use 2 types of reactors. One pressurized at high pressure of CO2, 2500 psi, and at those conditions CO2 exists as supercritical fluid. And then we use a low pressure reactor. Pressure is just 100 psi. And the reason for doing this, so here in the bottom I have an image of CO2 plume Conceptually, when you inject it close to the injection site, it's going to be supercritical, high pressure, high fugacity of CO2. And as you move away towards the edges of the plume, the fugacity is going to drop down. And fundamentally, the reactions are going to be different. It's not just the extent of reactions, but also products may be different as well. So we're examining those two regimes. Mancos Shale, here I have an optical image, and you can see, of course you cannot see because of the light, but trust me, it's really heterogeneous. It has visible lamination. You can see lighter and darker layering. And compositionally, those layers have the same minerals, but at different proportions. And I'm going to show you later what those are. And we took an unconditional approach. We're not using a simple brine. Instead of using, DI water or 0.1 molar sodium chloride, we actually matched composition of our synthetic brine to that observed in the field. So hence this crazy brine. It's mostly sodium chloride, but has significant amount of sulfate, which is characteristic to Mancos Shale and been reported in the field. And for this brine, the expected solubility of CO2 is 0.84 molar. So for our high-pressure CO2 reactor. And now to micromechanical testing. We have been performing microscratch testing to characterize changes in mechanical properties of shale, natural shale samples, following the alteration by CO2. And what it does, we have a stylus that we're applying at the known force to a surface of the sample, and we drag it along, creating a scratch. And we're measuring this transverse force as we're scratching it. And from the measurement of the force and the geometry of the scratch, the displacement of material, we do calculate scratch hardness and scratch toughness. And scratch toughness is related to fracture toughness, which is a measure of how easy it is to fracture something, how much stress you need to apply before you propagate fracture. And as a few speakers mentioned, shale is a very heterogeneous and anisotropic material, so mechanical characterization is difficult. So we've tried, here I have a representation of heterogeneous layered shale sample, and so scratching can be done parallel to bedding, as shown here. It can be done perpendicular to bedding, across cutting the bedding planes. And with this type of scratch, we can actually see the difference in the damage between different layers, but they're really hard to quantify. So what we ended up doing, and the results I'll be showing, are applying scratching along the bedding plane in this direction. So we can actually probe individual lamina, because the resolution of our method is sub-millimeter, and the layering is within a millimeter. So it's a really good match. So heterogeneity, going back to the issue of heterogeneity, as I mentioned before, mineralogically these layers are similar. There's no phases that are present in the lighter layer that aren't present in the darker. But when we use microfocus X-ray diffraction, we can see subtle differences between compositions. So, and as we move from the darker layer into the lighter, we see an increase in calcite and quartz. So it's more quartz calcite rich, and the darker layers are more illite muscovite and dolomite rich. And this is supported by our elemental mapping. We use micro X-ray fluorescence to map elemental composition. And I'm showing silicon, aluminum, potassium, magnesium, iron, and calcium. As you cannot see, but trust me, silicon is homogeneously distributed because there is roughly the same amount of quartz throughout. But aluminum, potassium, magnesium, and iron are more concentrated in the darker layers. So there's more dolomite, as we saw with the X-ray diffraction, and muscovite in the darker layer. And calcium is brighter in the lighter layer, so there's a little bit more calcite in that lighter quartz-rich layer. And this is aqueous chemistry results collected from different reactors. I'm showing high pressure CO2, low pressure CO2, and one of the control reactors. We always run control just to make sure we know what's going on when there's no CO2 in the system. And the changes here are really subtle. And remember, I mentioned that we started with a concentrated complex brine as close as possible to being in equilibrium with the shale. So our changes are subtle, but they're measurable. And we saw that there was a release of calcium, magnesium, and potassium. So we documented dissolution of calcite, dolomite, and muscovite, and they were more pronounced in the high-pressure CO2 reactor. And interestingly, we saw very low mobility of aluminum. Even though we were dissolving muscovite, we didn't see any aluminum in the aqueous phase, so it probably precipitated right back as an amorphous phase. So that may be important for geologic carbon storage if those aluminum phases can precipitate right away and clog pore throats and affect permeability. And again, another piece of evidence for dolomite dissolution is that we look at magnesium versus calcium, and we see linear correlation. And the dolomite in our sample was actually magnesium rich in member. And so when we sampled those reactors, we looked at both aqueous chemistry and the solid chemistry change at the same time. And here I'm showing results for the low pressure CO2 reactor, and we detected an interesting reaction going on. So these are XRD patterns for 4 samples for unreacted and then reacted under control conditions with nitrogen and under CO2, low CO2 pressure. And here I'm showing semi-quantitative results for the compositional changes. We're only quantifying major phases. There's many more than just 3 in shale, but those are the major components. And so Mancos shale was mostly quartz, calcite, and dolomite to begin with. In the control reactor, after 4 weeks, we saw some dissolution of calcite. And after 8 weeks, we saw further dissolution of calcite and a small amount of gypsum precipitating. But as opposed to control in the CO2 pressurized reactor, right? So again, we're starting with a lot of calcite. After 4 weeks, we dissolved almost all calcite. We have very little, so this red slice here left, and precipitated a lot of gypsum. But if we let the system go longer for 8 weeks, we precipitated calcite back. And in fact, at the end of the reaction, we have more calcite than we started with. So we have de-dolomitization reaction going on, which is replacement of dolomite with calcite. And now, after describing all those chemical changes, I'm going to show the mechanical characterization results. So of course, for chemistry, I use powdered shale, but for mechanics, I had to alter a whole piece of shale. And this is a CT scan of the shale puck. It's about 1 inch diameter, a centimeter thick. And if you look closely, you can see the alteration rim around the sample where it was in contact with CO2 and brine. And by characterizing the grayscale value, we can figure out the thickness of this altered layer, and it's about 1.6 millimeters, which is perfect because that's how deep we're sampling, about 1 millimeter with a scratch testing. So we're really just measuring properties of that altered layer on top. And here's just a photograph of different scratches. And again, as I mentioned before, we can see a difference between scratch depth on different layers, but hard to characterize. So actually, these results are from scratches that were imposed this way, so along the lamina. We probe every lamina separately. And so these diagrams, bar charts here, illustrate our results. On the left is the scratch toughness, and each bar is an individual scratch. So this group of bars here are for unaltered sample, light for the lighter layer, dark for the darker, and then this one's for the altered. And the same for hardness, calculated hardness. And what we saw, which we expected, but it was nice to also see it and quantify it experimentally, is that the lighter, the quartz, calcite, surprisingly rich layers, showed no weakening. They had exact same scratch toughness and hardness at the end of the experiment as they had in the beginning. But the darker dolomite and muscovite rich layers, they had a decrease in scratch toughness of about 50%, meaning that they're that much easier to fracture after the reaction. And to be able to extend those results long term, we created calibrated geochemical models. So we used our observations from the lab to construct these models, but we extended them to 5,000 years. So to roughly the duration we would need for geological carbon storage. And so again, this is on the left is the low pressure CO2, right on the high pressure of CO2, and I'm showing the percentages of different minerals in the system. And we're capturing de-dolomitization and precipitation of gypsum in the low pressure and hydrite and magnesite in the high pressure system. And interesting, so this is a table, but Interesting enough, when you look at the bulk values, there's not that much change because those are highly altered rocks. And in the models, I actually matched the fluid to rock ratio to what we would expect in the field. And we see very small difference in the mass and average density and hardness. But like I showed you just a minute ago, we see a high heterogeneous response, and we see significant weakening of just that one little lithophase. So overall conclusions are that those are the reactions that are triggered by the injection of CO2 are pressure dependent, and we see different products at the end of, depending on the pressure of CO2. So again, it's pressure-dependent reaction. We observed dedolomitization in the low pressure of CO2 reactor, and we think that dedolomitization process can actually be important for CO2 performance because it has been observed in other, at natural sites that are analogous to CO2 storage, where CO2 is actually seeping from the underground reservoir. And again, I want to highlight that the micromechanical testing is perfect for the investigation of this type of heterogeneous rock because we can probe individual lithophases separately. And we showed very clear localized weakening of the shale. Even though not even though, but our geochemical models predict small changes at the bulk scale, but we argue here that those changes at the local scale are going to dictate the performance of the cap rock. So, and in conclusion, if CO2 reaches a carbonate-rich shale cap rock, it's likely going to migrate along those more susceptible lamina. And the processes like dedolomitization may impact if you have a compromised cap rock with a fracture, those reactions may affect keeping the fracture open and serve as a positive feedback to CO2 leakage. Again, this was funded by DOE, our Energy Frontier Research Center. And before I'm out of time, I want to advertise this book that's going to come out next year. It's Science of Carbon Storage in Deep Saline Formations. And a large portion of this book is dedicated to coupled processes, chemical, mechanical, hydraulic, everything relevant to the science of geological carbon storage. Thank you. Do
we have questions for Anastasia? So I have a question. I think you said that when you did the scratch toughness test after the experiment, the quartz plus calcite layers didn't show any change. Did I get that right?
Yeah.
So why was the calcite in those layers not changing so that this fracture toughness or scratch toughness would have changed?
So yeah, I can speculate. Okay, speculate to that extent. So the mechanical weakening, it does not always, it's not a direct function of how much material has dissolved, because if calcite is present in more nodular fashion, it's not going to affect the mechanical properties. But if calcite is cementing grain contacts, if you remove material from grain contacts, then is when you see mechanical effects because the grain cohesion changes. So I think it's because of the spatial distribution and not the chemical identity of, in this case, calcite.
So just let me follow up since we still have a minute. So does this mean that every single rock you're going to have to test in this level of detail to make any kind of prediction?
And even then you might not be able to, because it's not going to be dictated by the matrix properties, right, but rather by their defects and pre-existing fractures. But I think there is hope. So I think if you can understand where the cement is located and what is going to be attacked by CO2, I think you can. If you there's been field studies where we can quantify that, okay, only 0.002% of calcite have dissolved, but we did see a difference in mechanical behavior because it was at the grain contact. So I think a more explicit accounting for the location of cement in the matrix would help with a more meaningful linking between chemical and mechanical responses.
Great, thank you.
Thank you.
Okay, if we can get our next speaker up here. And if you joined us late, we apologize. They don't know how to turn the lights off in New Orleans.
So that's why I'm wearing my sunglasses. It's
Oh,
like,
I forgot to introduce you.
Yeah, you better.
You're such a luminary. Dave Cole is going to speak to us about nanoscale pore features and fluid behavior in shale.
I've never had to give a talk when we were like simulating the surface of Mercury. It's not to discredit this great session. Thank you, Sue and Carl, for inviting me. I guess I have to figure out, do I click this and go? Yeah, so you've already heard a number of facets of what I'll touch upon. At least the early part of my talk, we talk about pore scale features. The back half of my talk, however, may be new to you, so stick around. There'll be a little bit of overlap in the beginning. So it's in two parts. First, we're going to look at pore features and talk a bit about what we're learning. We've heard some great talks already. So, you know, I start out with so very complicated but. Okay, so here we are trying to understand this very complicated heterogeneous Earth material. And how do we do that? And how well are we doing? And so there are a number of challenges associated with this whole business. First is, you know, what do these pore structures look like, both in reservoirs and seals? Because reservoirs contain lithofaces that contain high clay content. So it's not just about caprock, it's not just about shale, it's not just about gas shale. We see these high clay units in a number of different kinds of settings. And how do we quantify their size, distribution, and connectivity? And what about excess reactive surface area? Anastasia's talk sort of alluded to that a little bit. And there's a whole host of people working on this problem of accessibility of fluids and how they wet, and which fluids wet what kinds of surfaces. And how do these complex fluids actually behave at various length scales, particularly down to the nanoscale? So the back end of my talk will focus a bit on some interesting properties that we're learning about at that length scale. And finally, do these pores change during reaction? And so again, you heard Anastasia's talk allude to some of this. So we're kind of blessed in some way. We have a number of tools. I'm not sure you can read these slides, where we have different kinds of radiation that allow us to interrogate these materials, either optical, electrons, ions, and so forth. Electron microscopy being one of the principal ones we look at, dual beam fib, which you probably heard about. And also we have different fluid types we use to interrogate these pore materials, such as mercury intrusion and capillary pressure, which I'll allude to. So we have an armament of different kinds of ways to do this, all right? But nonetheless, it's a difficult problem area, as has been alluded to. This is a ternary of the carbonate, get this down here, quartz feldspar clay system. Can't see much on this with the lights and so forth, but again, we have this zone of sort of high clay, sort of ceiling type clays, rich rocks, and the brittle ones that actually frack that we want to get the gas out of. And we could actually plot all kinds of shales in this kind of part of the diagram, even at the high carbonate end. For example, in Ohio, we have a very high carbonate mudstone that actually hosts the shale, or hosts the gas rather. It's not really a shale, it's really a carbonate rock. So how do we deal with this? Okay, so the good news is we have a way to do this through these various tools. As I think Chris mentioned, deposition, environment, diagenesis, so forth, control the outcome here in terms of textures and pore features. And I want to kind of focus you on this part here. These are the kind of surfaces that we're worried about. If we want to start modeling interactions with fluids, these are the kinds of surface chemistry, silica, clay, carbonate, and organic we have to deal with. So just to give it kind of an example of, in this case, how neutron scattering is used to look at a particular mudstone. This is the Eau Claire, which Anastasia referred to. This is a very regional caprock in the central part of the United States. And so here we see three kinds of outcomes, depending on which lithophase you're actually in within this particular large caprock setting. So we have an oolitic shale, high percentage of nanopores. We have 1 nanometer right here, 10 nanometers, 100 nanometers. Then we look at somewhat different lithophases, glauconate-rich versus carbonate-rich. We get different distributions, different kinds of behavior. But one take-home message here I'd like you to keep an eye on is if you notice these humps and this little bit of dip, another hump, there's actually kind of a picture forming in our mind now about some of these shales, particularly the ones that contain high clay, that they are bimodal in terms of their pore distribution. You certainly get a sense of this with this kind of reach here and then a little bit out here, a coarser scale. The carbonate mud, we don't see that in. So again, we have this interesting kind of a scenario where we have somewhat bimodal distribution of porosity, again, based on how the rock is stitched together in its fabric. So we can look at what those kinds of features look like if we look at these mineral maps that we've taken with our SEM. Again, illitic shale, carbonate mud, and glauconite. And we see very different fabrics that then result in these very different kinds of pore distributions. I should say, if I go back one, this is total porosity now, not just connected porosity. This is total porosity. In this particular plot, I'm not sure you can see these, but we've got two kinds of pore distributions plotted on the right panel. The reds are from neutron scattering. Neutrons kind of pass through the whole sample and see all the pores. The mercury porosimetry, of course, only sees those that are connected pores. And so you kind of see that in this case of the illitic-rich material, we get sort of a fairly similar kind of map over between the two techniques. Why should this be? Well, the pore throats, which is what mercury porosimetry accesses, and the pores themselves, which neutrons see, are roughly on the same order of magnitude and size and shape. This is not true when you look at these other rocks that have a bit more coarser texture, such as a carbonate mud, or even a glauconite mud. You get really kind of very different patterns depending on whether we're talking about pore throat connectivity or the pores themselves. But the point here is we can actually start quantifying these distributions and their size distribution and their contribution to porosity. That's sort of the good news in terms of how to deal with a complicated earth material. Looking a bit deeper into scale, we can look at, this is the Eau Claire, this is our gas shale in Ohio, and you can see a lot of interesting features. Sue showed some of these with respect to the Marcellus. We have pores within the organic, we have clay pores, we have organic nested within clay, so a whole host of different kinds of features within this roughly few micron by few micron kind of 2D image. What we'd like to be able to do is look at this in 3 dimension. Of course, the question is this a representative volume? And so people are wrestling with this issue of when we start looking and teasing apart these particular features at very small scale, how do they scale upwards in terms of the full formation? That being said, we are blessed with tools that allow us to do this. So this is actually going to be a movie that shows a dual beam fib serial sectioning of this very small 20 by 20 by roughly 8 micron part of in this case, the Point Pleasant gas shale in Ohio. Okay, so you're looking at individual slices concatenated, roughly 500 or 600 of these that are going to show you that whole volume, that change in texture. The bright colors are the pyritic stuff, the dark is the organic. You can see the fibrous parts, which are the actual clay parts, as well as the coarser grains, which are either detrital or diagenetic. And so what dual beam allows you to do is then reconstruct this volume from different vantage points and allow you to look at that full volume in 3D, which is what you're seeing now, and then focus on maybe a particular kind of phase, like the green is the organic, and those amber and gold colors was the pyrite. So again, allowing us to look at this very detailed texture, but in a very interesting way. So we go beyond this one, go one more. Hopefully it'll let me go. Click over here, help me. I need to get off this guy. There we go. Go back one. How do I go back? So from that kind of imagery, we can then reconstruct the volumes and start looking at different kinds of associations. So what we have, what we have here are these sort of rendered volumes. In one case on the right is the pore volume within this volume, pore space. In the red is the organic kerogen. We can start looking at those associations, start correlating them in terms of where are they, how are they connected, and we can then start doing fluid modeling through this particular system with whatever computational fluid dynamics code you might want to use. Start this guy here. So again, it's not that jerky really, it's supposed to be smooth. Anyway, and it won't fall apart, trust me. So at a higher length scale, we're even blessed with some really relatively new technology. These are images from the Nanoscale Center at Oak Ridge. These are helium microscope images, again, to ratchet down in scale to look at the complexity. But we're now blessed to be able to see this complexity. So on your right is a helium microscope image of a framboid stitched together by this kerogen, so you can kind of see that association. And quite often we find the pyrite reduced material with the organic, actually. And on the right panel, you see the illitic carbon kind of matrix mix, and you can see pores, actually pores within pores. Again, as Sue pointed out, these pores are actually circular, okay, in terms of their geometry, but the illite pores are actually very plate-like. So again, very interesting geometries that we have to deal with if we want to model these. So I'm going to change gears now. Simply, we know that nanoscale is important here, and we've been able to kind of interrogate it. Those of us that have thought about thermodynamics for a long time have to rethink our view of thermodynamics, particularly bulk thermodynamics, because we're at a scale where bulk thermodynamics doesn't apply. the magnitudes change, the directions change of how fluids behave at interfaces. And so I think Christophe sort of talked about this a bit in his talk. So, you know, you can take almost any kind of property you can imagine in a fluid, whether it's thermophysical or transport, interactions at interfaces, or even dynamical information such as translational, rotational, librational motion. They're all impacted by an interface or by this reduced dimensionality across the board. Okay, I won't go through the whole list. The good news is we have tools to interrogate these length scales. And on top of that, we have molecular dynamics or density functional theory that allow us to actually quantify and underpin you know, these sort of observations we might make in the lab with you know, real molecular kind of level understanding. So in our group, we've kind of taken a threefold approach to this. We kind of do our detailed characterization with whatever tools, scattering, microscopy, whatever. We also try to do sort of in situ fluid matrix experiments, NMR, X-ray, neutron scattering, whatever, and then combine that with 3D modeling and simulation to kind of give us that robust view of what's happening to a fluid in a particular porous kind of environment, Earth environment. So just to kind of benchmark this for you, imagine now you're a pore, you're a slit pore, or a circular pore, and you've got a fluid inside that's trying to react or try to behave in a certain way. So imagine you've got densification at a surface, maybe less dense out here in the center of the pore, and as pore size changes, you all can kind of get a sense of that absorption layer, interaction layer starts to take on, you know, more of a meaningful impact as you start to reduce the dimensionality from, say, 10 nanometer pore to, say, 2 nanometer pore. So again, the relative contribution of fluid behavior is going to scale depending on that size of those pores and the pore volume itself. So I'm going to show you just a few examples, a few vignettes of outcomes to kind of give you a sense of what we're learning. This is gravimetric experiments that we did on a whole host of different kinds of earth materials and engineering materials to look at water uptake versus P over P0. And P over P0 is pressure changing toward pressure of saturation. P sub 0 is Psat at that particular temperature. In these cases, a couple of different temperatures, silica pores, pillared clay, carbon, and chloride. The take-home message here is these different kinds of pores, different kinds of surfaces give you a really different kind of water wetting, water uptake kind of outcome. You can see for the pore glass and even for the carbon, you see very little uptake early on at modest pressure until you get this rapid rise, which really indicates condensation, pore condensation. Conversely, look at the clays and the chloride, you see sort of, you start building layer, single layer, monolayer sort of early on because there is a stronger attractive force between water and those charged surfaces. You show the different images here, what these things look like. So, you know, this is a macroscopic measurement, but it's giving us really microscopic information if you think about these kinds of interactions and the shape of these particular curves. Case in point, we'll take a look at the carbon case. Notice they go back one, you'll see this shape right here. We have very little coverage and then a capillary condensation. You'll see in this one here, this is sort of the simulation that we ended up getting. But we did a very straightforward grand canonical Monte Carlo simulation of carbon, of water in these kind of different kinds of carbons. We decorated it with carbonyls and some defects to give it a more realistic, natural look. Used certain kind of water model, and they had different thicknesses of the different pore sizes. Anyway, what we're going to see in the video is how this fills and how it desorbs during the process of filling at 100 degrees centigrade. So we go ahead and click this guy. The first thing you're going to see is the very larger slit pores start to fill fairly early on, and then the narrower pores. Okay, and as it dewaters, you're going to see the opposite. You're going to see the thick water in those thicker layers, the thicker pores hold on to itself, and then they'll dewater last. And so we actually were able to emulate that absorption curve very well, which you see in the lower right. It's just one example of several that we've done like this. So when we look at just comparing carbon and methane, it's a take-home message here for a hydrophobic surface like carbon. We see really different kind of behavior, which then will impact how we imagine transport and flow. So for water and a carbon, we see this kind of clustering outcome in terms of how the water actually is contained within these pores at the nanoscale, compared to methane, which gives us sort of a layering kind of effect. So then one can imagine, well, how this might impact recovery of gas when you use water to frack a particular shale that contains organic carbon or carbon high content pores, as we showed early on. So kind of interesting outcome, interesting kind of concern that we might have in terms of how to actually model this. Another kind of interesting take-home message that I'd like you to leave with that you're not familiar with is that the nanoscale solubility of these non-polar species actually increases. So on this panel here, you see the solubility versus bulk pressure. This is a simulation, classic molecular dynamic simulation. Methane solubility increases almost 60-fold over bulk water at bulk water solubility of methane, and aluminum and MgL put not quite as great an impact. So you ask the question, why? Well, there's a number of factors that control the solubility of a particular constituent in water, particularly at a nanoscale, and part of it is the degree of hydrophobicity, structure of water, and the timing of these fluctuations at this length scale. So you see for silica, for example, you look at the density of water on that surface, you see a lot of dark blue. The dark blue is a very low density regions on that surface, and so very few high density kind of clustered areas. This allows open space. These low density water regimes offer open space for methane to kind of occupy it and kind of increase that solubility. Of course, this changes as the hydrophobicity changes. So we learned actually a very interesting outcome here that this length scale, depending on that surface, we're going to have a different kind of behavior for methane in terms of solubility. It's also true for transport, which I'll get to in a minute. But here's a case of water in a silica pore. Okay, so we can imagine, so what happens here in terms of the actual structure that's changing within this pore? It's a silica nanopore, 1.6 nanometers. Again, another simulation that we did. And you can kind of see these regions right in here. Maybe not, well, we get these water bridges that form across this pore and impeding the actual transport of methane, actually encapsulating that methane in this kind of region here. This is at high water loading. We start changing that water to gas ratio, as we see in the next guy. It lets me switch, hopefully. Where we have a little bit lower water to gas ratio, even the 30-40% change, and we see a lot different kind of behavior. The methane, in this case propane, are these blue dots, blue balls moving through this water. Silica is this matrix, and so now we have a somewhat enhanced transport, enhanced solubility, if you will, as it turns out, because there's more space for that methane to occupy that pore. So again, a very interesting outcome that we've been able to predict from MD. Finally, I just want to talk about diffusivity. This is kind of another take-home message. There's no time to set these calculations up to describe to you. But again, under reduced dimensionality, we have reduced diffusivity. So if you look at bulk water on this panel here, we're kind of at the e to the minus 10 meters squared per second. So for bulk system, we'd be up around 2.5, actually, way off scale for water. Of course, it changes as the surface changes, all right? As we look at methane within a water-filled pore, we also see this variability and diffusivity, again, based on the hydrophobicity of that surface, the structure of water at that surface, and how that fluctuations of water in and out of that surface as it fluctuates between the pore wall and the interior of the pore affects solubility. So again, starting to get a sense of the mineralogic control as well as the dimensionality control. So a few take-home points. First, we sort of talked a little bit about the availability of a number of really nice methods to interrogate these materials at various length scales, 10 orders of magnitude, in fact, neutron scattering and so forth. We've sort of touched upon the fact that in some shales, particularly the high clay-rich shales, we're getting this bimodal distribution. Polar versus non-polar fluids actually respond differently under nano confinement, as we sort of touched upon. Methane exhibits this incredible solubility increase, and these local properties of water affect this outcome in a really major way in terms of considering the behavior of gases in the subsurface. Thank you.
Thank you.
I want to do this, but you wouldn't let me.
We're out of time, unfortunately. Thank you. You're not allowed to come back up here, Dave. Okay, and for the last speaker of this session on shale, everything shale, we have hydraulic fracturing in shales, the spark that created an oil and gas boom. John Olson, welcome.
Thank you, Susan, and I want to thank you and Carl for inviting me for today. So I'm going to talk a little bit about the economic impact or the energy impact of shales currently, and then talk a little bit about hydraulic fracturing related things, which is a subject that my group has been working on the last few years. I don't think I need to go through that. So just to give you an impact of how shale oil and gas production has affected the U.S. energy production history. So this is from 1920s to 2017. So this is almost 100 years of oil and gas production. We peaked in the 70s. This little blip right here is discovering, or the onset of oil from the North Slope of Alaska, which was considered to be this stupendous, incredible boom of extra resources. And I just put this on here to show that this is where the shale boom started. And just to compare it to Alaska, which involved huge amounts of improvement in technology and billions of dollars of investment, the shale boom, at least currently, we don't know how long it'll last, but has dwarfed the impact of the North Slope of Alaska. So this is a really big impact on U.S. oil production as well as world production. If you look at this on a state-by-state basis, and here I'm going back to the 1980s up until present, and this is, I forgot to say what the unit over here, this is in barrels per day, so we're going from 0 to 3.5 million barrels of oil, crude oil production per day. So if you look at Texas, Texas had the same declining trend. People thought it was just going to keep going down forever, and it was the end of the oil age. Shale production basically resulted in a tripling of oil production from reservoirs in Texas over about a 6-year time frame. Another state that was significantly impacted by this, and there's all sorts of impacts that you have, but this is North Dakota in here. And you can see California and Alaska, which are two big producers, really have not been very affected by this. So there are certain states that are very rich in shale that have had a great impact in oil. If we look at gas, this is kind of interesting. This is in gas in billions of cubic feet per day. I'll equate this to an energy term in a minute. You may be looking, I think I even have a metric conversion on the next plot, but if we look at billions of cubic feet per day from 2000 to 2016, the first real shale project that worked was the Barnett. So that's what this curve is right here. So they've been producing gas out of the Barnett for probably over 20 years, but it really didn't start to kick up until 2004 or so, and this is also when the price of gas went over $10 per MCF in the United States. And then the Barnett kind of leveled off. This took a drilling of 15,000 wells to get up to this level of production. And I'm just going to mention one other here, which is the daddy of them all, which is the Marcellus. So here you can see the Marcellus really dwarfs every other shale play in gas in the United States. And we're up to equivalent of 17 billion cubic feet per day. This is actually last year's production. I don't have this year's production. And what is that equivalent to? So if you think of a natural gas power plant has about a 40% efficiency of turning energy content into electricity, this represents about 85 gigawatts of potential electric power generation. So a big impact on our energy picture. If you just take a quick look internationally here, who are the big players in gas production? The United States was going to start importing natural gas about 10 years ago before this, or 15 years ago before this shale revolution occurred. So here's the United States, which has always been a top gas producer. Here's Russia, which is kind of the second most, and here is all of the Middle East, is this line right here coming up and been increasing since the 1990s. And here we are, I changed units unfortunately here. This is in trillions of cubic feet per year, not per day. So if you translate that into BCF per day, I think this number for the United States is on the order of, I think it's 90 BCF per day. But this right here, this bump in production in the United States is all, unfortunately I covered this up with some words, but this is all from shale, and just shale production in the United States exceeds all of the gas production in Europe. So this is a European curve right here. And this is just a comment from the International Energy Agency, basically saying the U.S. is not just going to affect its own gas market, but the LNG market, which is a worldwide market. So we're really, what's going on in the United States is really having a big economic impact. So we just go back to one slightly smaller scale. If we go back to the Barnett and look at a well-by-well impact. So this is a curve showing production in, if you're not used to oil field units, I'm sure you're loving this, but this is thousands of cubic feet per day. And so this right here would be 1 million cubic feet per day, this 1,000, okay, and this is 10 million per day. And this is individual wells. This is data downloaded for the Railroad Commission of Texas. This red line right here is a vertical well that was hydraulically fractured in the Marcellus in 1996. It still produced, whoops, actually I did the higher rate well first, I'm sorry. So this is a multi-frac horizontal well, started out about 10 million barrels, or 10 million cubic feet per day. It's down to 4,200 or 4.2 million cubic feet per day. What's the difference between horizontal wells and vertical wells? It's about a factor of, something on the order of 10 to 100 in this particular case. But we can see this, even this vertical well that was hydraulically fractured is still producing about 100 MCF per day. These units may not mean much to you, so I translated them into electricity again. So 2 years into the production of this horizontal well, we're still getting 20 megawatts worth of power out of it. This 20-year-old gas well in the Barnett is still producing about a half a megawatt. And there's that, like I said, there's in the United States, there's hundreds of thousands of these wells. So they're significant contributors. So the reason why this stuff has been successful, these are all old technologies, but combined in new and ingenious ways, but horizontal wells, horizontal drilling and hydraulic fracturing. And then the U.S. is blessed with abundant shale, but many other places in the world are as well. Why is it just working in the U.S.? Part of that is really logistics and political climate. Now, you could argue the political climate changes a lot, but the U.S. has been probably the most amenable to development. But really, it's a logistical track to get this to work. So if we just look here, those of you who aren't familiar with this process, typically we drill anywhere from 5 to 15 wells on one pad. Drill a vertical well down, if we're talking Marcellus, maybe 8,000 feet, and then might drill 5 to 10,000 feet horizontally. And multiple fracture treatments are essentially start at the toe of the well and work back towards the heel, and do this and pretty much cover the entire subsurface with a fractured rock that's artificially fractured. The optimization of this, the reason why this has worked so well, the drilling costs have really come down. I was talking to someone from EOG, and they said they can drill an 18,000 foot measured depth well in 4 days. So 8,000 foot vertical, 10,000 foot lateral in 4 days. And main reason why you can do that so fast is they've got bits that will last through that entire process. They don't have to switch out their bits. And they also have mechanized motors down hole that can change direction of the drilling. So you don't have to put in a different set of equipment for vertical wells versus horizontal wells. And so what about the more geologic aspects of this? So if you think about hydraulic fracturing in shales, a lot of what we think is different is its hydraulic fracturing in naturally fractured reservoirs. And this diagram right here, which is from a paper by Fisher et al. In 2004, this is a map view. This is, I think this is in feet, 3,000 feet by 3,000 feet by 3,000 feet. Here's the treatment well, and this is a vertical well again, but just the idea of what's going on. All these little gray dots are microseismic events, which we're locating probably not the hydraulic fracture itself, but some natural fractures to the sides of the hydraulic fracture that are slipping and generating magnitude -3 to -1 type earthquakes. And if you look at this through time, they interpreted that there was some dominant trend northeast-southwest of fracture growth, hydraulic fracture growth, but there are also these cross fractures. And then they had killed wells all around. Normally we'd think the hydraulic fracture is maybe a 1/4 inch wide and it runs, maybe 500 feet to either side, symmetric, a single plane. Here we've got a zone that's like 1,000 feet wide and 3,000 feet long that's affected by this treatment. Killed well means basically water went into that well and stopped the gas production. So we know that at the depth of stimulation here, which is about 7,000 feet, we had this wide zone. So what does this mean? Well, one artist rendition of this is, if you think this is another map view, these black lines are joints or natural fractures. We're fracking from the north to the south. The hydraulic fracture, which is fluid driven, hits one of these natural fractures that's diverted along it, and then it kicks off and breaks into 2 fractures and 4 fractures and 8 fractures and expands in its broad zone. And so this is really revolutionary concept of a different way that hydraulic fractures propagate, and we really feel like this all happened in the 2000s when we worked in shale. One thing that's interesting from a philosophy of science or history of science realm is this is actually a 1987 paper from Warpinski and Teufel talking about hydraulic fracturing in tight gas sandstone. So it really took almost 20 years for this concept of multi-stranded hydraulic fractures to really be accepted once the geophysicist finally said that we have some data that confirms that. So it's a very interesting history of science thing. And so how do we work on this? One of the things that is very important in this, things like stress shadows and how the mechanical fracture interaction occurs. There's a bunch of different models. Some of them are continuum based. like this grid model. Some of them are mapping individual fractures, like this model down here, which is similar to something we've worked on. But that's a challenge, and in order to get these models to work, we have to look at what's going on in the crack tip, right? Crack tip and the broader poroelastic and elastic deformation in the reservoir. And so, so what I want to do before I talk a little bit about crack tip, which I'll just have a couple slides because I don't have that much time, I want to show what do people see in the subsurface. So one of the things we can model all day long, but we want to see some real data. So there's actually an interesting experiment that was done by ConocoPhillips, and actually there's a DOE-sponsored one that's just being completed that has been tight data, but they're supposed to start releasing that data. But in the Eagle Ford Shale, which is predominantly an oil producer, but also a gas producer in South Texas, they did microseismic monitoring, distributed acoustic, temperature, and sensing, where they put fiber optics on the outside of the casing, and also monitor wells. And this is the interesting thing. They actually drilled and cored through pre-frac and post-frac. And I just put this up here because it's a very interesting data set. It's not my data set, but this was presented in August. But this is a treatment well down here. This is a vertical cross-section. The treatment well down here, and they drilled all these additional horizontal wells on either side and crossing and veering through. What they were looking for was the hydraulic fractures. And I just want to show there's a microseismic data set. This is a map view now, and they have multiple horizontal wells. That's what these black lines are. And the frac jobs were crossing in this direction, and they mapped where the microseismic went. And I can't, in this diagram, it's kind of hard to show whether it was broad or narrow, but you can see if you look at the vertical cross-section, which is the bottom of the figure, everything was pretty well contained within the treatment zone. And so that's one of the things these diagnostics do, is tell you whether you're actually keeping the frac where you think it's supposed to go. But if we look at some of the cores through here, it's very interesting. Here's a 1-foot scale for the core, then I have a 10-foot scale for the resistivity image log. We can see fractures that were, since this is pre-frac and post-frac coring, these are fractures that were creating during the frac job. We're about 75 feet away from the treatment well in the hydraulic fracture direction. And you can see that cluster here. Here's some more. And so all of these fractures are basically coming from some fairly narrow 1 or 2 foot thick zones that were perforated. And so the idea is, how can you propagate fractures side by side in this way and get this clustering? And so that's a big problem that we're working on in our modeling realm. But that stress shadow effects, it's kind of a puzzling result. Now the interaction here, they're thinking these are new fractures, not reactivated natural fractures. And they do part of that evidence by seeing evidence of gel and proppant that are in those fractures. If I go on just to two quick slides here at the end to say, so we've got these large-scale observations, which that's an incredible data set. It's really hard to explain. So one of the things we've done is looked at cracks propagating through naturally fractured rock. And this is actually a result of a, I can't remember the name, the test where we've got a dual, we're basically loading on the top here, and we've got two rollers here, and so we're basically driving a crack up through this sample of naturally fractured Marcellus. And so we had this tensile crack propagating across these veins. You're looking down on the top of the bedding plane. And we see basically approach angle is important, but what I'm showing you here is we go from a pure 0.01 inch, apologize for the English units, to a 0.075 inch thick vein. In one case we cross, the other case we divert. So basically the idea of what is the strength of these fractures, these natural fractures, and whether they impact hydraulic fractures is one of the things we're looking at in the small scale. And I don't have the thin sections here, but you can see things like dislocations and also pre-existing fluid inclusion trails can impact the propagation of this tensile fracture. If we look at that was a laboratory unconfined specimen. We can actually create synthetic blocks, and other people do this with blocks of real rock. We do this at the 1 foot cubic block scale. Some people do it at the meter scale that have larger budgets than we do. But so we basically create a hydraulic fracture well in here. And so here, if you break this block open post-testing, you can see here's my well bore. I'm injecting and creating a fracture that's propagating in this plane. The fluid is dyed red, so that's my hydraulic fracture. And you can see that as a fluid propagation direction, which is parallel to our maximum horizontal stress direction, we embedded a cemented vein basically made out of this hydrostone and plaster combination of synthetic material. The hydraulic fracture gets diverted along that pre-existing fracture, and then when it gets to the tip, it kinks off and comes back to the normal direction. One of the things we're surprised at, which we should have known beforehand, but we were surprised at, is this is truly a three-dimensional process. So our natural fractures are typically not as tall as hydraulic fractures. And so where the natural fracture was, we got diversion, but we also got a significant amount of the frac job just went beneath or above this natural fracture obstruction. And so that three-dimensionality was an important lot. So to predict these kinds of fracture propagations, we really need to have a good idea of basically what is the natural fracture system, and much of the pore scale stuff that we've heard so far this morning would also have an impact on where the fluids go. And so just to summarize there, that was kind of a whirlwind tour of some of my impressions on the hydraulic fracturing impact in shales, that this has really made a huge difference in oil and gas production in the U.S. Hydraulic fracturing is not new, but we're getting to understand more and more how little we understand about how it works. And really what we're doing today has really been developing for 30 years, I would argue. And natural fractures are a very important aspect of that. And then the post-fracture production side, as far as the pore structures and the porosity and permeability you've heard about through most of the morning, that's a huge impact on whether these wells are economic and how they contribute to our energy infrastructure. Thank you.
And we have time for questions.
I noticed that the fractures seem to be sub-meter spacing in that core that you showed. Is that typical? And how much of the gas are we getting out of the first go? And should these things be shut in and left and reactivated or refract? Will we get more gas?
Okay, so let's see if I remember all that. So the spacing of the fractures, I think, this is a fairly scarce observation here about what do the fractures look like far away from the well. Typically, the initiation points of the fracture are spaced, well, they started out spacing those initiation points 100 feet apart. Now they're coming down to maybe even 25 feet. A modeler like me would say that once you get far away from the wellbore, you can't have them that close together because of their stress shadow interference, and this observation would nullify my impression. So I think we have a ways to go on that, but there are some stress shielding type things from fracture mechanics where you can grow clusters of fractures that are very closely spaced. I've worked on that in the natural fracture world, so I think there's some concepts that we can do, but I don't think we know what the typical spacing is. As far as now I've already lost. Oh, let's say how much of the gas do we get out? I think reservoir engineering estimates I've seen are something on the order of maybe 15% or something of the gas is produced. A lot of that is how much is contacted by the fracture system and how far does it have to travel. Shut in, there are some ideas about when you pump some fluid down, actually it appears that particularly in the Montney in Canada, they find that when they shut in and let the well so-called soak, they actually get a better production. So there's some wettability, other kinds of geochemical processes going on that impact when getting the gas out of the shale that I think people don't really understand as well. But there are some shut-in things, and they do actually go in and refract these sometimes as well. So there's a lot of that going on.
Another question? I have a question. I thought it was interesting, the experiment you talked about in the Eagle Ford, where they were actually coring through pre-fracked areas, and I mean, that's really interesting. Can you just talk a little bit about it? Like, who's paying for that? Will there be core available? Is that a proprietary study, or is that like an open kind of thing?
Okay, so I just saw the paper, so but I know some of the people involved. So that experiment I showed you was ConocoPhillips. I'm not sure that they'll make their core public, although I know we at the University of Texas are going to do some testing on their core, so they'll pick partners. But the DOE-sponsored experiment, presumably that will be public core and the data will be public, and it'll be much more open than presumably that particular experiment, ConocoPhillips. ConocoPhillips paid for all of that. And maybe they had a partner in there. The DOE was a combination between industry and DOE funding, and so I think that data set will be more widely distributed and accessible to experimenters.
Okay, Dave.
Yeah. HFTS, hydraulic fracture. Yeah, so the hydraulic fracture test site is the name of the DOE-sponsored project going right now, which is in West Texas in the Permian Basin in the Wolf Camp. There was also an experiment West Virginia did in the Marcellus. And then if you want to go really far back, that Warpinski and Teufel paper, that was a GRI and DOE-sponsored experiment where they cored through tight gas sandstone and saw multiple fractures and did some experimentation. So there's... That's GTI now at Gas Technology Institute, I think.
Thank you. We have to stop now.
Yep.
All right, so this, excuse me, concludes our session. Thank you. I hope you've been able to see the connections from the first talks and from the nanoscale right up to this broader scale. Tomorrow we have another oral session in the morning. It's called Shale from Fracking to Forest. I think that one sort of similarly spans this whole range, but there's some water quality posters or talks and posters. The posters will be in the afternoon. So it's session EP21H in the morning and session EP3C in the afternoon. And I think the morning session's in a smaller room and maybe they'll turn the lights off. So thank you, everybody, and thank you to our morning speakers.